Find the flow rate in gallons per minute. In this problem, water is pumped from reservoir 1 to reservoir 2. Both reservoirs are open to the atmosphere, and the elevation difference of their water surfaces are given. Properties of the suction and discharge piping are provided, as well as the pump curve, which has an operating range between 1,400 and 2,400 gallons per minute. Taking a closer look at the graph, the pump curve is plotted against the system curve, and the pump will operate at the flow rate where these two lines intersect. The problem statement provides data points for the pump curve, and points on the system curve can be calculated based on the head loss seen by the system at various flow rates. The possible solutions are the flow rates 1,600 to 2,200 gallons per minute. Since the pump curve minus the system curve is monotonic, it would be prudent to first evaluate one of the two middle flow rates, 1,800 gallons per minute or 2,000 gallons per minute. If we evaluate 2,000 gallons per minute, and the head loss in the system equals 165 feet, then 2,000 gallons per minute is the correct answer. However, if the system head at 2,000 gallons per minute is greater than 165 feet, then the actual flow rate is less than 2,000 gallons per minute. And if the system head at 2,000 gallons per minute is less than 165 feet, then the actual flow rate is more than 2,000 gallons per minute. Now it's time to solve for the system head at a flow rate of 2,000 gallons per minute. The system head for a given flow rate equals the total head at reservoir 2 minus the total head at reservoir 1 plus the head loss through the system between the two reservoirs. Since both reservoirs are open to the atmosphere and static, the pressure head and velocity head values are 0, and the equation reduces down to the change in elevation head plus the head loss through the system. The change in elevation head equals delta H, 150 feet, and the head loss through the system equals the major losses along the pipe wall plus the minor losses caused by the fittings, valves, and entrance. In the head loss equation, the problem statement provides the diameter as 8 inches, or 0.667 feet, through both suction and discharge pipes. We also know the total length of pipe is 720 feet, as well as the gravitational acceleration, g, equal to 32.2 feet per second squared. But we don't yet know the friction factor, F, the velocity, v, in feet per second, or the sum of the minor head loss coefficients, sigma k. We'll first solve for the velocity. The velocity equals the flow rate divided by the area, where the assumed flow rate of 2,000 gallons per minute is converted to cubic feet per second, and the area is calculated from the diameter. The velocity of flow equals 12.77 feet per second. With the velocity solved, we'll next determine the sum of the minor head loss coefficients. The problem statement identified the system as having a sharp edge pipe entrance, a check valve, and two standard 90-degree elbows. The head loss coefficients for these three items are looked up and added to the table. Since there are two elbow fittings, we'll multiply the quantity of each item by its k value and find the sum, which is 4.60. The last variable to solve for is the friction factor, F. The friction factor is determined using Reynolds number, the relative roughness, and the Moody diagram. Reynolds number equals the velocity times the diameter divided by the kinematic viscosity. We've already solved for the velocity and diameter, and the kinematic viscosity for fresh water can be looked up in a table based on its temperature. For 60 degrees Fahrenheit, the kinematic viscosity equals 1 times 10 to the negative fifth feet squared per second. The Reynolds number equals 7.02 times 10 to the fifth. The relative roughness equals the roughness distance, epsilon, divided by the inside pipe diameter, d. Based on the pipe material, the roughness can be looked up in a table of values, and for steel, the roughness equals 2 times 10 to the negative fourth feet. Knowing the diameter already, the relative roughness computes to 3 times 10 to the negative fourth. With knowledge of Reynolds number and the relative roughness, the friction factor equals 0.016. With the friction factor solved, all variables on the right-hand side of the equation are known and plugged in, and the head loss between reservoirs 1 and 2 at a flow rate of 2,000 gallons per minute equals 55.4 feet. By knowing this head loss, the total head in the system while operating at 2,000 gallons per minute equals the 150 feet of elevation head plus the 55.4 feet of head loss due to friction, which equals 205.4 feet. So far we have one data point on the system curve at the flow rate of 2,000 gallons per minute and the head of 205.4 feet. From the pump curve data, we notice that at a flow rate of 2,000 gallons per minute, the head loss is only 165 feet. Therefore, the pump curve passes below the data point on the system curve. This means the actual flow rate is less than 2,000 gallons per minute, ruling out solutions C and D. Solutions A and B were 1,600 and 1,800 gallons per minute. However, when considering our data point on the system curve, we can rule out the 1,600 gallon per minute solution because as flow rate decreases from 2,000 gallons per minute to 1,600 gallons per minute, we would also expect the head to drop from 205.4 feet to a lower head value, as would happen if the pump were operating at 1,800 gallons per minute. When reviewing the possible solutions, the answer is B.